So there's that one group of metals where the metals always form just the same kind of ion. So, and those are groups 1A, 2A, 3A, zinc, and silver. So zinc is always a +2 ion. And aluminum's always a +3 ion. Sodium is always a +1 ion. Their charges are predictable, and so their ion names are just their names. Then there's everyone else. All of the other metals can form more than one ion, an ion with more than one charge. So iron can be +2 or +3. So we can't just call it iron ion because we need to know which one. So it's a little bit like, the kings of England, King Henry. Well, which King Henry? King Henry IV, King Henry V, whatever. So we use Roman numerals just like the kings of England. So you take the name of the cation, it's just the element name, and the Roman numeral is the charge. It's the charge on that ion. And then that will be in parentheses following the name. There's actually no space between the name and the parentheses. There is a space here and then the name of the anion. If you are writing a name from a formula, then you're going to have to figure out what the charge on that ion is, and you can do that by looking at what the charges on the nonmetals are, and we'll go over that. So let's do this example. Here's CrBr3, and we need to name this. Well, this is an ionic compound, right? Because the first element is a metal. So boom, ionic compound. So we're going to name the metal ion first because it comes first in the formula, and then we're going to name the nonmetal. So Cr is the abbreviation for what element? Chromium. I'm going to write chromium. And then I'm going to ask myself, is chromium in groups 1A, 2A, 3A, zinc, or silver? No. That means it needs a Roman numeral because we can't predict its charge. I don't know what that Roman numeral is. I'm just going to put parentheses here and save some space. And I'm just going to go on, and I'm going to name the anion. Bless you. What do we call bromine as an anion? Bromide. So in my chemistry land, this is the guy, this is the girl, they're getting married, she changes the end of her name. It makes sense to me. Okay, now we need to figure out what the charge on that cation is. Now some of you, this is easy peasy, and for others of you, it can be a bit mystifying. It's only difficult because it's strange, and you haven't done things like this before. If I put it in terms of little boys and cookies and moms and plates of cookies, you'd be like, oh, duh, of course. But because it's ions, then your brain kind of wigs out. So what I'm going to do here is I'm just going to draw the ions that are present in that formula. The Br3 tells me there are 3 of those bromide ions, right? There's no number after the Cr, which means there's only one of those, and there's 3 of these. Now I'm going to put the charges on the bromide ions. What's the charge on a bromide ion? -1. So they are each -1. So my total negative charge then is -3, right? 3 negatives once, so -3. In order for this to be a neutral compound, which is always what it's going to be, where all of the charges add up to 0, if this side is -3, this side has to be +3. So here I need +3 charge, and that's going to be distributed over 1 ion. So that means that the chromium must have a +3 charge. Everybody following me on that? So the Roman numeral for 3 is 3 capitalized. So that's chromium 3 bromide. Any questions? We need the formula to refer to one specific compound. We need the name to refer to a single compound. If I said chromium bromide, there's more than one compound that would fit that description. So we need the Roman numeral to specify the ion charge. Let's do a couple more examples. Let's name this compound. Well, his name is Fez, obviously. Well, is it an ionic compound? Yeah, because iron's a metal, right? So I know so far all we've talked about is ionic compounds, but we're going to get away from that pretty soon. So what's the name of the element with the symbol F? Yeah, it's iron. Does iron need a Roman numeral? Yes, it does. I know it needs a Roman numeral because it's not in 1A, 2A, 3A, zinc or silver. My goal is to say that so many times that all of you will remember it. 1A, 2A, 3A, zinc or silver. Those guys do not have Roman numerals. All other metals as cations need Roman numerals. Okay, so S, sulfur, and we change the ending of the name to sulfide. Well, why isn't it sulfuride? Because it isn't. If you wrote that, I would laugh at you privately, but I wouldn't mark it incorrect because that's one of those little weird things. Okay, how do we figure out what the charge on the iron is? We need the charge on the sulfur, right? This one's a little simpler. Here I have one iron ion and I have one sulfide ion. We find the charge on the sulfide ion, and so we know that the iron must be 2+. Okay, so it's 2+, so I'm going to put the Roman numeral 2 here. This Roman numeral is the charge on the ion. It has nothing, well, it is not a subscript somewhere in the formula. It is related to the subscripts because of the balanced charges. But sometimes students will think, well, there's a subscript 1, it should be iron 1. No, it's not the number of those atoms. It's the charge on the ion, okay? And then let's go the other way, write the formula for ruthenium 4 oxide. Well, what's the element symbol for ruthenium? Ru. A good guess is the first 2 letters. And what does that 4 mean? It's the charge, right? This is a metal, so the charge is positive. When we're writing the formulas for ionic compounds, you need to write down the individual ions with their charges first. And so oxide, that's from oxygen. What's the charge on oxide? -2. So this is 2-. So multiple ways of thinking about it. And probably all of you are thinking about it in different ways. It's RuO2. You see why? So we have a +4 here and a -2. We want the smallest number of ions that when we bunch them together, their charges will add up to 0. Now, if you're a fan of the crisscross thing, you could do crisscross here, and crisscross will get you Ru2O4, which is the correct ratio, but it's not the simplest ratio, right? And so we would want to reduce 2 to 4 down to 1 to 2, okay? So this is an example of where crisscross could get you into trouble. The other way to do it is to just think about, okay, what's going on here? I've got ruthenium 4+, I've got oxide, and I need to figure out how I can get the totals to be the same. Because right now I've got +4 and I've got -2. You can't change the charges. All you can do is add ions. So I need more negatives. I'll add one of these. And then this gives me a -4 charge. So now I have a +4, -4, those added together give me 0. And so my formula needs 1 ruthenium and 2 oxygens. So this is the correct formula right here. Any questions? What if we have polyatomic ions? It's the overall scheme of naming is the same. You name the cation and then you name the anion. But this time the anion has a name that's not just directly from the periodic table. It's something that needs to be memorized. And almost all of you passed your memorization quiz, so you've at least got a fairly decent handle on the common polyatomic ions. So as it says here, names and formulas of polyatomic ions must be memorized. That's just it. You gotta memorize them. So if we look at this compound here, NaNO2, I look at that and I ask myself, well, is that first element a metal? Yes, it is. So this is an ionic compound. Ionic compounds in Chem 1A always have only two different ions. One cation, one anion, right? So the sodium is the cation, and everything else must be together as one anion. Sometimes students want to say, well, that's sodium nitride dioxide or something. Well, it's very creative, and I could probably figure out what you're telling me, but nomenclature is not something that where we value creativity. Okay, here we value following the rules, doing it all the same. Okay, so we need two ions only. So the first one is sodium. The second one is everything else, and we memorize the name of it. Okay, sodium nitrite. So this is a useful table from your textbook. As you are working through homework and worksheet problems and stuff for this chapter, I would encourage you to always try to do the polyatomic ion from memory first, and then check your work. So it's like, acetate, what was that? And try to do it, and then look it up. If you always just go straight to a table and look it up, then you're not going to remember it, and I'm not going to give you this table on a test. Okay. What we see here is that most of these polyatomic ions contain oxygen. So here we've got oxygen, oxygen, oxygen. Here's one that doesn't. Ammonium, that is the one oddball polyatomic cation. Ammonium. Here we've got cyanide. Cyanide doesn't have oxygen in it. But most of the others have oxygen. So those are called oxyanions because they're anions that have oxygen in them. Many of these occur in a series where you could have sulfur with oxygen, and the numbers of oxygens could be different. So instead of coming up with just, a name for each of these, we'll call this one Steve and that one John, right? The names follow a pattern. So when there are two or more ions in a series, we use the endings to indicate the numbers of oxygens. So the one with more oxygens ends in 8, the one with fewer ends in ite. So examples here are nitrate and nitrite. If you look at these formulas, one's NO3 with a -1 charge, one's NO2 with a -1 charge. The only thing that's different is how many oxygens there are. The number of nitrogens is the same, the charge is the same. In the name, the only thing that's different is that last letter, the third to the last letter, nitrate or nitrite. Okay? Here we have sulfate and sulfite. There can actually be 4 different ions in this series. And then we add some prefixes in. So here we've got chlorate. Chlorite has 1 less oxygen. And then this one, ClO minus, well, we're going to keep this fewer oxygen suffix, and then we're going to add a prefix as well, hypochlorite. Hypo means below. You know what a hypodermic needle is, right? Where does it go? Below your skin. Hypodermis, below skin. If we have extra oxygens, so we've got chlorate with one more oxygen, this is perchlorate. Per is a prefix that means more. We're a little more familiar with it as hyperactive, right? More active than usual. So perchlorate has more oxygens than usual. Chlorine and bromine are in the same family in the periodic table. They're both members of the halogen family in group 7. I think of them as sisters. So bromine and chlorine are sisters, and they react with oxygen in very similar ways. So this is chlorate. Bromate has the same formula, it's just a different sister in there. It's bromine instead of chlorine. So if I memorize the formula for chlorate, then I can figure out what the formula for bromate is. And this also works for iodate. Iodine, what would the formula for iodate be? So this is IO3 negative. So we can make these oxyanions for the halogens just by swapping out the halogen element. Okay? So this summarizes kind of my trick way of doing this. So you memorize the eights. So that would be things like chlorate, nitrate, sulfate, phosphate, the ones that end in 8. You memorize those. So here's chlorate. We're going to memorize that one. And then we can sort of derive the other ones just by looking at the prefix and suffix and what those mean. So this is chlorate. If we add another oxygen, the charge doesn't change, just the subscript and the oxygen. We're adding another oxygen, we're going to call that perchlorate because it's hyper, it's got more. If we take away one oxygen from chlorate, this is the light version. Bud Light has 1/3 fewer calories than regular Budweiser, right? Chlorite has 1/3 fewer oxygens than regular chlorate. It's the light version. And then hypo is below chlorite, it's one less. And just to note, this is upside down of how it's shown in the textbook. It's correct, both places. I just think of up as being more. So I like to put perchlorate on the top instead of on the bottom. Any questions? So let's practice using polyatomic ions. So let's name this compound. The formula is SnClO2. Now, we hadn't seen parentheses in a chemical formula before. We've seen them in the name around the Roman numeral. Here we have the parentheses around this ClO3. I think of these parentheses as being a little bit like the shrink wrap that they put on bundle packs of things at Costco, right? You go to Costco and you want a bottle of ketchup. You can't just buy one bottle of ketchup. You can buy 2 bottles of ketchup that are shrink wrapped together, or you can buy ketchup, mustard, mayo, and pickle relish all shrink wrapped together, right? But you can't just get a bottle of ketchup, right? So the parentheses here are like shrink wrap, and the number on the outside is telling me how many groups of that do I have. So this is like a bundle pack, ClO3. It comes as a unit, parentheses, and on the outside 2, telling me I have 2 of that unit, of that polyatomic ion. And we need the parentheses because without the parentheses, that looks like 32 oxygens, right? Or we'd have to do something like this, Cl3O6, and then are we necessarily going to recognize that that's chlorate ion? No. So both of these are confusing. And so when you have more than one polyatomic ion, you put it in parentheses and put how many on the outside. We don't do that for all of them because we only do it when it's needed. If you have a single ion, single polyatomic ion, it's not confusing, so we don't need to put the parentheses on there. Okay? So when we're naming this, the first element, is that a metal? Yeah. What's the name of that metal? Tin. Does tin need a Roman numeral? Yes, he does. He's not in groups 1A, 2A, 3A, zinc, or silver. And then we're going to look at what's in the parentheses, and what's the name of that? Chlorate. And we know that because we memorized it. We find the charge for the parentheses there by looking at the charges on, well, the charge on the anion and the relative numbers of them. So I've got, in that formula, I have 2 chloride ions, and I memorize the charge is -1 on each. The formula, I'll erase that box so we can see it a little better. The formula is showing me I only have 1 of the tin ions. So if I look at these, I say, well, I've got a total of -2 charge there. I need a total of +2 charge here. And there's only 1 of those, so it must have the +2 charge. This figuring out the charge and figuring out how to put the ions together is something that a lot of students struggle with, because you never worked at it until it clicked. Once you see it, it's very straightforward. It's a pattern, and there's no complicated math. It's multiplying and dividing very small whole numbers. So if this is just like, I'm not sure how you're doing that, you need to practice and ask a lot of questions, okay? And I will answer as many questions as you ask. So that one's tin 2 chlorate. How about this one? Write the formula for cobalt 2 phosphate. Writing the formula, we need to write the ions with their charges first. What's the charge? Well, first of all, what's the symbol for cobalt? CO. And it's important that that's a little o, because we don't want this to be confused with carbon monoxide. So small o. And this 2, what does that tell me? It tells me the charge. It doesn't mean that there's 2 cobalt ions. It means the charge is 2. And then what's the formula for phosphate? PO4, 3 minus. So we've got the ions with their charges. Now we have to figure out how many of each of them do I need so their charges add up to 0. I'm looking for the least common multiple of 2 and 3, which is 6. So I need to multiply this one by 3 and that one by 2, and then they'll add up. I can do the crisscross thing here. Always make sure that these numbers are not the same. And you always have to check and see at the end if it needs to be simplified. Or I can draw it out. So drawing it out, I see I've got +2 and -3. So I need more positive charges. All I can do is add another one of those. So now I've got +4. I got too much positive, so I'm going to add more negatives. That's a 3. So then this is -6. And then they're like, well, dang, we're just going back and forth. Add another one of these. There we go. +6 and -6. I'm going to count them up. I have 1, 2, 3 of those. CO, 3, and I've got 2 phosphates. So I've got PO4. It's a polyatomic ion, and there's 2 of them. So to avoid confusion, I'm going to shrink wrap them and put the 2 on the outside. If I did crisscross, this 2 would come down here, this 3 would come down here. Least common multiple is 6. I need to multiply 2 by 3 and 3 by 2 to get 6. Any questions? Being able to write a formula like this is something that's pretty important in Chem 1A, because we're going over how to do it, and then the rest of the semester we're going to assume that you can do stuff like this. Some ionic compounds, when they form crystals, they will incorporate a particular number of water molecules into their crystals. And so this is different than just like having wet salt. Here there's a definite ratio, a definite proportion between the ions and the water molecules. Not all ionic compounds do this. Nicely, you don't need to know which ones do. Here are 2 examples. This is the hydrated form, because when you're hydrated, you've got enough water in you, right? So here, this is cobalt 2 chloride, and for each of these formula units, there are 6 water molecules in the crystal structure. Over here, this is called the anhydrous form, an meaning without, hydrous, without water. So this is without water. This is just the ions cobalt and chloride. And you can see that the color is different. We can take this hydrated form, and most hydrates, if you heat them gently, you can get the anhydrous form. Sprinkling water on this will not get you the hydrate back all nice and pretty. So what we need to be able to do here is we need to be able to write names and formulas for hydrates. Epsom salts are something that you may or may not have soaked your feet, sprained ankle in. The formula for Epsom salts is MgSO4.7H2O. It is very important to understand that that dot is not a multiplication sign. You cannot multiply some ions by water molecules. They are not numbers, right? So there's no multiplication involved. What that dot means is that these guys go together. This is a hydrate. So this is magnesium sulfate, and then here, to specify the number of water molecules, we use Greek prefixes. The Greek prefix for 7 is hepta. So that's magnesium sulfate, heptahydrate. You name the ionic compound the same way we just learned, and then you add the number of water molecules. So this guy, COCl2, naming the COCl2, cobalt is one that needs a Roman numeral. And we get the Roman numeral 2 because we know that the 2 chloride ions each have a -1 charge. So cobalt 2 chloride, and then for 6 we put hexa and the word hydrate. So these are common Greek prefixes, and these get used lots of different places in science. So mono is 1, di is 2, tri is 3. There are other prefixes for these numbers, right? Bi means 2 as well. It's important to use the correct one. Tetra is one you might not be familiar with. Tetra means 4. Penta, hexa, hepta, octa, you should be familiar with those from the gons, right? The hexagon, polygons. So the prefix tells you how many sides they have. An octagon has 8 sides. And then there's this one, hemi. Hemi means half. So a hemisphere, that's half of the globe, right? A hemisphere, it's a half sphere. So let's practice a little bit. Let's name these hydrates. We've got CaSO4.12H2O. Well, naming these guys, we've got calcium. Does calcium need a Roman numeral? No, it doesn't. And then, so we named calcium, got that guy out of the way. Then everything else, the SO4, has one name. What is it? Sulfate. So we name that part. And then the prefix for half is hemi. And then for water, we write hydrate. So we just go through the name and name the pieces. Let's do this one. Yeah. Yeah. Calcium chloride. And then what do we do for the 2? Di. Dihydrate. Very good. Calcium. Just try to spell it right. It's an I. I'll just fix it. IU. Calcium doesn't need a Roman numeral. And so then we'll just go to chloride. So we've got calcium chloride. For 2, we write di. That's this part right here. Hydrate. That tells me it's calcium chloride with 2 water molecules.
Okay, but you see that little 2 by chloride, we just ignore it.
Excellent question. What about this little 2? That little 2 is important. We don't need to include it in the name, though, because in an ionic compound, it's the charges that tell us how many of the ions we need. And so here we've got calcium 2+ ions and chloride 1- ions. The reason that there's 2 of those is that you need 2 to balance the charge on the calcium. We don't need to specify that in the name, though, because we can figure it out because we all know the charges on the ions. It's an excellent question. Students want to, stick a dye in there or something, and you don't need to do that. So we also need to write formulas. Barium hydroxide octahydrate. Well, this first part is an ionic compound. Barium is Ba. What's the charge on barium ion? Yeah, +2. It's in group 2. We should be able to tell the charge. There's no Roman numeral here, so we're going to have to look at the periodic table. Hydroxide. OH minus. Because you memorize it. And it's always OH minus, it's never HO minus. So then we're going to look at the charges on these to figure out how many of each do I need. So I need 1 barium and 2 hydroxides. Because this is a polyatomic ion, it's got more than 1 ion in it, and I'm going to have 2 of them. I need to shrink wrap them together. So I've got the shrink wrapped hydroxide here, and I put the number of hydroxide ions on the outside. So I've got 1 barium and 2 hydroxide ions. And it's 1 to 2 because of the charges. And then I'm going to put a dot, and the prefix octa means 8. So 8, that's a regular sized 8, followed by the formula for water, H2O. Barium hydroxide octahydrate. Okay. Naming and writing formulas for hydrates is not an essential part of Chem 1A. If you just get the ion thing down and you blow this off, you'll be okay, right? If you want the A, you better learn this, though.